Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 28th lecture. In this lecture, we will be discussing timing driven optimizations. In the earlier lectures, we had seen that logic synthesis consists of various tasks which are shown in this slide, and in earlier lectures, we had seen or we have discussed RTL synthesis, logic optimization, and in the last lecture, we had looked into technology mapping. So, at the end of technology mapping, we get a net list which is in terms of standard cells of the technology libraries. And in the last lecture, we discussed that once we have a net list in which the cells are from the technology libraries for which the transistor level implementation is defined, the PPA of the design can be estimated. For example, the area of the circuit, the timing of the circuit, and the power dissipation. These things can now be, after technology mapping, we can estimate these quantities well. And therefore, after technology mapping, what we do is that we carry out further optimizations. Now, since we can carry out timing analysis also after technology mapping, because we have library cells, and from the library cells we can compute the delay of the cells and get fair idea of what the critical paths are in our circuit, then we can target or we can optimize our design for timing, right. So, that is what the purpose of timing driven optimization is, right. So, after technology mapping, we know the timing of our design fairly well, though the interconnects are not there in the design, yet cell delay can be computed fairly well, and based on that we can find what are the critical paths in our design and whether we can improve or we want to improve the timing of some of the paths, and then we do some targeted timing optimization on those paths. So, that is what timing driven optimization is, and this will be, and we will be discussing this in this lecture. So, first let us look into the flow of timing driven optimization. So, in timing driven optimization, what we have our design is, the design is a mapped netlist, right. So, mapped netlist or netlist is in terms of cells of the technology libraries, and that is why we are saying that it is a mapped netlist. And then we also give the information to the we give the information of the technology libraries from which the cells were picked in the mapped netlist to the tool, right. And then we also give the constraints using the SDC file, and then using these three inputs we can run an STA or static timing analysis, right. So, to do timing driven optimization, first thing we need to do is that carry out timing analysis or static timing analysis, and for that we need three inputs: the libraries, the map netlist, and the SDC file. Now, once we do STA, then we can get that get the information of what are the critical paths in our design, whether there are some negative slacks that needs to be fixed, and those kind of information we can get from STA. Now, once we have done the STA, then we can first check whether the timing target is met. Maybe our slack target was 0 picosecond, or it was say plus 10 picosecond. Note that after technology mapping, we may want to do timing driven optimization, and our slack target may be more than 0 picosecond, because at this point of time, if we have not done physical design, the interconnect delays cannot be computed directly, and therefore, some sort of margin must be left for the interconnect delays also, and that is why we may want to have our slack target more positive than 0. Right. So, depending on whatever the slack target was or the timing target was for our model or for our design, we will first check that. If it is met, right, if the timing target of our design is met, then we need not do anything. We need not worry, our design is, we need not perform any timing driven optimization, right. So, it goes into this path. If the timing target is not met, then what we do is that we identify targets. And what do we mean by identifying target? we want to know which paths in our design are critical, where we want to actually apply the timing driven optimizations, right. So, those targets must first be identified, the paths, the logic gates or the cone of logic gates where we need to perform some optimization. So, we need to identify those targets, right. So, once the target is identified, then what is done is that the timing driven transformations are applied, right. So, some logic, some optimization techniques are applied or transformations are applied to our circuit. What are these transformations? We will see in the subsequent slides, right. And once we have applied the transformation, then we carry out incremental STA or incremental static timing analysis. And what does incremental static timing analysis do? It carries out timing analysis in only a small part of our circuit. So, our circuit may consist of say millions of gates, but we have made some small change in say one of the logic cones in our circuit. We will not want that we carry out STA for the complete design, which will be taking lot of run time. Rather, we will want that the timing analysis is done only in the area or in the region where the timing optimization was done and where the timing is changing, right, that or delay and the arrival time and the slacks in our design is changing in the portion of the design. We want to carry out timing analysis only in that area, and to do that we perform what is known as incremental static timing analysis. It will not perform static timing analysis in the complete design, but in a small portion or logic cone of our design where the transformation has impacted the time. And after we have done the incremental timing analysis, then we say that check whether the timing target is met, right. Whether the timing target is met, meaning that after, because of the applying the transformations, the timing might have improved and now we are meeting the target, right. If it is meeting the target, then we exit that loop of timing optimization. This is the loop of timing optimization, right. We exit the loop of the timing optimization if the timing target is met, or if no possible improvement is possible, maybe that we have put some limit on the that how much improvement, how many times of how many trials of transformation we want to apply during timing driven optimization, or some criteria to check whether improvement is possible in our design or not. If that criteria is met, meaning that in now we are now condition is met which says that the no further or not significant improvement of timing is expected by doing this kind of transformation. If that criteria is met, then again this loop is exited, right. Now, we carry out these transformations iteratively, and if these two target these two condition, meaning that either the timing target is met or no further optimization is possible, if that is hit, then it exits the timing optimization loop and it goes into what is known as area recovery. So, once we do timing driven optimization, what happens is that the timing of our design changes, and it may happen that in some portion of our design the timing profile has improved such that now there are scope of or the slack has become so positive. More example, may that slack may become say plus 1000, right, just an example, right. So, if the slack is too highly positive, then there is some scope of maybe improving the area, right. Why there can be scope of improving the area? The reason is that what happens is that typically whenever area is decreased, right, area is decreased meaning that area is improved, the timing degrades, timing or delay goes on increasing, right. So, delay and area those goes in the opposite direction, right. So, if there is a the timing if in a portion of a logic cone the timing profile has improved such that the slack is highly positive, it means that we can afford to increase the delay, right. We can afford to increase the delay, right, and as such we can also improve the area. We can minimize the area as a result of that, if the delay increases slightly, we still have sufficient margin that timing target will not will be become bad or not will get be affected, right. So, after we have done the loop of timing driven optimization, a phase of area recovery is carried out, in which we try to improve the area in the region of the circuit where we can afford to increase the delay, right. And once the area recovery phase is also done, then we then the tool will the implementation tool will produce the timing optimized mapped netlist. So, this is the basic flow of how the timing driven optimization is done. Now, we will be looking into that what are the various kinds of transformations that can be applied in timing driven optimization. So, we have seen in the earlier lectures that libraries contain cells of same functionality, but of different sizes. For example, an inverter can be of size 1x, where x is some arbitrary unit of area, and it can have a cell of size say 2x and 4x and so on, right. Similarly, for other types of logic gates. So, library contains cells of same functionality and different sizes, right. Now, the size of the cell increases, then what happens that when suppose we are considering this inverter and 1x inverter and 2x inverter, then what will happen in 2x inverter? The transistors that are used to implement the inverter, that will be of larger size, right. So, the W by L width will be larger for the transistors, the width will be larger for the transistor in the implementation 2x compared to 1x, and it will be further larger in 4x, right. So, width of the transistor becomes larger. As a result, what happens is that the size increases, right, and the size of the cell increases, and the other thing is that the delay decreases. Now, why does the delay decrease in this case? The reason is that if W by L of a transistor increases, then the current that is driven by that transistor increases, right. So, current is proportional to W by L, and if W by L increases, the current increases. And therefore, if this inverter, suppose this inverter was connecting or driving a load of value CL, then because of the bigger transistor in 2x compared to 1x, this 2x inverter will charge this capacitor faster, and therefore, its delay will be less compared to 1x, and in 4x the delay will be further reduced. Now, in resizing, what we do is that in resizing we change the size of the cell, but keep the function of the cell as the same, right. So, we replace an AND gate with an AND gate, but of say larger or smaller size. So, that is what resizing is. So, in resizing we replace a cell C1 with another cell C2 that produces the same Boolean function, but has different size. Okay. So, let us take an example. So, let us assume that there is a cell C1, right. Let us assume for the sake of illustration that C1 is an inverter, right. So, suppose this one is an inverter, right. This is C1, and what we are saying is that we replaced it with functionally equivalent cell C2 of a larger size. So, now we replaced it with a bigger size inverter, right, whose name is say C2, right. This is what the resizing is, right. So, we change the size of the cell. Now, because of changing this size, what effects do we expect, right. Suppose this cell was driving another cell, say D1, right. So, we are changing the size of C1, but not of D1, right. So, here also we will have a D1, right. D1. Now, because of larger size of C2, and because C2 is comprising of bigger transistor, larger transistor, it will be able to drive this load, right, corresponding to this wire, and the input capacitance of this inverter D1, there will be some load capacitance here, right. Now, if we consider this timing arc, the delay of this timing arc will be smaller for C2 compared to C1, right. So, delay and output slew of C2 can reduce, right. So, here the delay between the arc between, let us call this pin as A and this as Z. So, between A and Z, the delay will decrease because C2 is of larger size, and therefore, it will drive the the load quickly, and its delay will decrease. And the other important thing is that its output slew will also decrease. So, if it was rising slowly, right, the output at when we replace it by C2, it will rise sharply, right. So, the output slew will also be decreasing in the case of a big, if we use C2 of a larger size. And as such, if the output slew decreases, what happens to the delay of the transistor D1? Now, in the earlier lectures, we have seen that the delay is a function of output load and the input slew. Now, when we increase the size of C2, what happens? We increase the size of this cell, right? We use a bigger cell C2. Then what happens that the output slew decreases, and therefore, we expect that the D1 delay of D1 will also come down. Why? Because the input slew has become lower compared to if there was C1 instead of C2, right. So, because of this replacing C1 with C2 of larger size, we expect that the delay and output slew of C2 will reduce, and the delay of cells in the fan out of C2 can also reduce, meaning that delay of D1 can also reduce, right. And there will be other effect on the input side, right. This is the good effects in timing or in delay that will happen in the C2 and in its fan out, right. But what will happen in the fan in of that we need to consider that also. Now, suppose this C1 was being driven by an inverter of size of whose name, let us take the name as say B1, right. Now, we are not changing the size of B1. So, B1 will also be driving C2, right. So, this is B1, right. Now, what impact of resizing of C1 will be there that will be seen by B1, right. Now, what will happen at B1 is that earlier it was driving a cell C1 which was of smaller size, now it has to drive a cell C2 which is of larger size, and therefore, the input capacitance of the pin A in this case compared to this case will be lower, right. So, if we make a bigger cell, that is we use a bigger cell C2, the input pin capacitance of A will be larger, right, and therefore, B1 will needs to drive a larger load, right. And therefore, what we expect? We expect that the delay of B1 will go up, right. Delay of B1 will go up. Why? Because delay is a function of load and input slew. Since the load has increased on B1, the delay of B1 will increase, right, and also the output slew of B1 will increase, right. The output slew, suppose here the B1 signal was rising like the output at this point, B1 was rising like this. After we have resized, its slew will increase and it will rise at a slower rate, right. Now, what impact this increased output slew can have? It can actually increase the delay of C1 or C2, right. So, the delay and output slew of the driver of C2 can increase, and the delay of the cells in the fan out including that of C2, suppose there was another gate in the fan out, right. Let us call it as E1, right. Here also you have E1, right. Now, the delay of E1 will also get impacted. Why? Because the output slew of B1 has increased. So, the delay of E1 can also increase, right. So, delay of the cells in its fan out including that of C2 can increase, right. So, what this example illustrates is that if we increase the size of cell C1, right, the delay can decrease in C1 and in its fan out, but delay can increase in its fan in, and because of the output slew the delay of the resized cell can also increase, right, and in the fan out of the driver of the resized cell there also the delay can increase. So, these two effects are in opposite direction. The first effect is actually decreasing the delay and the second effect is increasing the delay. Now, if we resize, we have to pick an optimum, right. So, if we go on increasing the size of C1, at some point the second effect will be overtaking the first effect and we may not get the required benefit of resizing, right. So, increasing the cell size will not always yield to improvement in delay, right. So, the tool needs to do and do or pick the size of the cells more intelligently, right. So, the tools use some algorithm to find an optimum size of the cells and use it for timing driven optimization. Now, let us look into another optimization technique which is known as restructuring. So, in restructuring or rewiring, what we do is that the timing critical signals are moved closer to the sinks in the cone of logic to reduce the overall path delay. So, let us take an example and understand that what do we mean by moving timing critical signal close to the sink, right. Consider this circuit, right. So, there are 3 AND gates and the arrival time of the signal at A is 40, at B is 70, at C is 20 and D is 30. Now, out of these 4 signals, which one is most timing critical? The one which is most timing critical is this, right, which is coming at B. Why? Because the arrival time is maximum for this, right. So, now what is the worst arrival time at this point Z, right, or the maximum arrival time? So, the maximum arrival time is, if we consider this path, the delay of all the AND gates, we have assumed it to be say 50 time units and we have taken time units as arbitrary numbers, right. So, suppose we consider the path A to Z. So, what is the delay from A to Z? 50 plus 50 plus 50, 150 plus 40, 40 is the arrival time. So, the arrival time at this point through A will be 190. Through B, how much it will be? 150 plus 70, that is 220, right. Now, out of 190 and 220, 220 is the worst, right. For others, there are only 2 AND gates. So, 50 plus 50 plus 20, that is 120 and 50 plus 30 is 80. So, for others are not critical. The critical path is this, right. So, the critical or the worst path is this, right. So, we will want to move B closer to the sink. So, the sink here is Z, right, where the signal is ending, right. So, how can we do that? So, we can just do the rewiring, right. So, we can put the signal which is coming at B directly to this gate, right. Since this is all of them are AND gate, right. So, whichever signal is applied at which of the ends does not matter, right, and therefore, we can move the signal which was coming at B closer to the sink, right, and then the one which is having the next arrival time, that is 40, right, and then 30, then 20. So, now let us see what is the arrival time. So, for this path, what is the arrival time? 20 plus 150, that is 170, right. For the other path, from this we have 180, right, 30 plus 150, that is 180. So, the worst is 180. Now, for this path, we have 100 plus 40, that is 140. So, still 180 is the worst, and for this path, we have 50 plus 70, 120. So, the worst is now from C sorry from this. So, the worst, the path which is exhibiting the worst arrival time or the maximum arrival time is this, sorry, is this, which is exhibiting an arrival time of 180. So, from 220 we have improved the arrival time to 180 by rewiring. So, this is a simple case, because all these logic gates are of same time AND gate, right, and therefore, if we move any of them, these are it does not matter, because at this end the function is symmetrical, right. So, this is just a 4 input AND gate, right. So, that is what. So, therefore, we can put any signal at any of the end, the functionality is not going to change. But what if this box that is shown here was having any arbitrary function, right? If it was any arbitrary function, then how can we do the restructuring? Let us see. Okay. So, let us suppose that y is the output produced by a combinational logic function f, and it depends on the signals x0, x1, x2 to xn, right. So, these are the inputs and it is a combinational logic, and let us assume that the x naught is critical, right. Suppose whatever the most critical out of it, sorry, out of all the inputs x0 to xn, the one which is most critical, let us call it as x0, right, and this is the path which is most critical, and f is an arbitrary combinational function, right. So, y is equal to f x naught x1 x2 to xn, right. Now, what if x naught is critical, what do we want to do? We want to move x naught closer to the output y, right, we want to move closer to the y. How can we do it? So, let us see. So, how to the problem is how to restructure the circuit such that the worst delay of the circuit improves. So, the arrival time at this point y improves, that is what our target is, right. So, what we can do is that we can do Shannon expansion, whatever this function was f, we can do a Shannon expansion with respect to x naught, right. So, to do Shannon expansion, what we have seen earlier, that we need to put the value of the variable as 0, right. If we put x naught as 0, then we get a function f naught which is the negative cofactor, right. So, this is negative cofactor, and then we put the value of x naught as 1 and we get f1, and f1 is a known as positive cofactor, right. Now, once we got negative cofactor and positive cofactor, we can implement this function in terms of multiplexer and these cofactors. How we can implement? We can implement like this. So, we use a 2 to 1 multiplexer. So, this is a 2 to 1 multiplexer in which in the select line we have x naught, right. On the select line we have x naught. So, whenever x naught takes a value of 0, this f naught should be produced. So, now we implement f naught, right, and if the x naught is taking a value of 1, then we select f1 or the positive cofactor, right, and the combined result of this selection is that what y will be nothing but y is equal to x naught bar f naught plus x1 sorry x0 f1, right. So, this is what what this implementation is implementing, right. Now, let us take an example, then this concept will become more clear. Suppose we were given this circuit, right, this circuit, this is the combinational logic circuit in which we have an AND gate, we have an OR gate, right. Let us assume that the delay of the AND gate is 25 in some arbitrary timing units, and delay of OR gate is 20, right, and the delay of the multiplexer is 30. We will be using multiplexer later on. So, the delay is specified, right. Now, let us look into the arrival time profile. So, arrival time at A is 30, arrival time at B is 100 and arrival time C is 40. So, at the point Z, what is the worst or maximum arrival time? First, let us take this path, right. In this path, we have one AND gate, right, 25 plus 20, right, that is 45 plus 30, right. So, in this path the arrival time will be 75. Through the other path we have 100 plus 20 plus 25, that is 145. And for the third path we have 40 plus 20, that is 60. So, out of this the worst is through the B, right. So, the worst the maximum arrival time is through this, right, and the arrival time is 145, right. Now, can we reduce this arrival time by making some transformation in the logic? That is what the purpose of this restructuring for timing driven optimization. So, to improve the arrival time at the node at the output Z, we need to move this signal B closer to the output, right, and therefore, we need to do a Shannon expansion of this circuit with or the logic function with respect to the function B. So, first let us see that what Z is implementing. So, Z is implementing AB, right. So, this is AB, so this is AB and this is an OR gate. So, we have AB plus C. Now, we want to do a Shannon expansion of this function with respect to B. Why with respect to B? Because this path through B was the most timing critical, right. We want to improve the timing of that path. So, what will be the negative cofactor of this? For that we need to set B is equal to 0, right. So, if we put B is equal to 0, Z becomes C, right, and if we make B is equal to 1, we get the positive cofactor, right. So, if we make B is equal to 1, then become A plus C, right. So, that is what. Now, with this cofactoring, now we can do the implementation using mux, and so the implementation will look something like this. So, now the signal B is going to the select input of the mux, right, and on the 0 side we have the negative cofactor, that is C, and on the one pin we have the other cofactor, that is A plus C, right, the positive cofactor, that is A plus C implemented using this OR gate. Now, let us evaluate the arrival time of this. So, the arrival time at C is 40, it is already given here, right, B is 100 and A is 30, right. Now, if we consider this path, what is the arrival time? The arrival time is 40 plus 30 is 70, right. If we consider this path, again 30, sorry, for this path we have to take this one, right. So, 40 plus 20 plus 30, so 30. So, the arrival time will be 40 plus 30 70 plus 20, that is 90, right. Then we have to see the other path, right. The other path is through this 30 plus 20 plus 30, right, is equal to 80, and the third one is from this through this and this 100 plus 30 is 130, right. So, the worst arrival or the maximum arrival time is 130, right. So, what we have done is that we have moved the late arriving signal, that is the B, right, closer to the output by doing factoring using Shannon expansion theorem, right, and as a result the arrival time or worst arrival time decreased from 145 to 130, and therefore, we have improved the timing of our design, right. Now, what will be the cost involved? The cost involved can be in terms of area, right. So, it may happen that F0 and F1, which are the cofactors, if we implement them, then there can be the number of logic elements in implementing F0 and F1 may be larger than the original circuit, and therefore, there will be an area penalty, or the area of the circuit can increase in this kind of transformation. Additionally, we have used, say, if there are, say, n inputs in this logic cone, right. Here it was only 3 inputs A, B, C. If there are multiple inputs, then we can do it recursively. If we pick the first one or the last arriving signal and do a Shannon expansion with respect to that, and then we pick the next late arriving signal and do the transformation with respect to, or carry out Shannon expansion with respect to that variable, and so on, and we can do this recursively. Now, let us look into another optimization, which is known as fan out optimization. So, in fan out optimization, what we do is that we insert buffers in high fan out net to improve the timing or other characteristics of our design. Suppose this was our circuit, right. So, there is a gate G, right, in which the output is driving many logic gates, right. So, suppose there were k pins which were driven by this logic gate G. If if k is large, then the load that is being driven by this gate can be much higher, and therefore, the delay of G may be very large, right, and we may want to reduce the delay of G, right. Then how we can reduce the delay? Suppose out of all the sinks, that is P1, P2, P3, P4 to Pk, the P1 was most critical. Suppose this path was most critical. So, what we can do is that we can add a buffer on for the other rest of the sinks, right. So, we add a buffer B1 which is driving P2, P3 to Pk, and the P1 which was timing critical, that is directly driven by this gate, right. So, now as a result of this transformation, what will happen? The load on G gate will reduce. Why? Because earlier all these loads were seen by the gate G. There is all these loads P1, P2 to Pk was seen by the gate G, and therefore, the output capacitance that was being driven by G was much higher, right. Now, what happens is that the output capacitance that is driven by G, that will be lowered. Why? Because now the capacitance that will be seen by G will be because of this P1, the pin P1 and the B1, that is it, right. The other loads will be shielded by or that will be driven indirectly by B1, right, and therefore, the delay of G is expected to decrease, and the timing of the critical path is expected to improve, right. Now, if there are more signals which are more critical, then we can add more buffers in these. So, now suppose B1 is still suffering from large delay, and there are some path, for example, P2 is also next critical, right. If P2 is also critical, then we can again shield the rest of the sinks from B1 by doing a next level of buffering, and so on. So, what are the downside of this transformation? The downside is, of course, the area taken by the buffer B1, and also the path, the delay of the path P2, P3, P4 to Pk, the delay of the path going through these pins will encounter the delay of the buffer B1 also, and therefore, the timing of the other paths, that is through P2 to Pk, that can actually degrade, right. So, that is another thing that we need to take into account, right. Now, this high fan out net optimization can also be done to fix the load violations and also slew violations. For example, assume that the output slew of the gate G was very high, right. It was rising very slowly, such that the max transition violation was there on this net, or if the load that was driven by G was so high that the max capacitance violation was encountered by G. Now, in that case what to do? In that case we can add buffers to this net, to the net A or this net N, and as a result of that the slew and output slew violation and the max capacitance violation can be fixed. How we can do? Let us see. So, we can add two buffers B1 and B2, right. Now, suppose there were say 100 sync pins, right, P1, P2, P3 to P100, right. Suppose there were 100 pins in the fan out, right. So, what we can do is that we can add two buffers B1 which is driving 50, P1 to P50, and B2 is driving 51 to P51, sorry, P51 to P100. So, we have distributed the fan out in with two buffers. Now, again if this load is high, for example, P1 to P50 is still high, we can further divide by adding more buffers, right. So, we can divide it into two more buffers. So, here we will add two more buffers, each driving a load of say 25 sinks and so on. So, this can be done recursively. Now, again here what penalty we are incurring? The penalty is in terms of area, right. So, there will be area and also power dissipation associated with the new buffers that we are adding in our design. Now, let us look into one more transformation which is known as retiming. So, what do retiming do? Retiming balances the amount of logic between registers. So, let us take an example, then it will be clear. Suppose this is a portion of our design which is the critical portion, right. So, in this assume that for the sake of analysis, let us assume that the skew clock skew is 0, right. Assume that the ideal clocks are coming at all the clock pins, right. So, in that case the setup constraint will be decided by the data path, right. So, in this case the data path delay is say 500 plus 50, right, from this path, from this FF1 to FF3, 500 plus 50. So, it is 550. The other path is 400 plus 50, so 450, and this path is 400, right. This is the delay of this path is 400. So, these are the delays, right. Now, out of 450, 550 and 400, the maximum is 550. So, the clock frequency that which this clock circuit will work will depend on the critical path, right. So, the critical path is this, right, and its delay is 550. So, if the clock skews are assumed to be 0 and the clock to Q delays are assumed to be 0, setup time are assumed to be 0, just for the sake of illustration, let's assume them to be 0, then what maximum clock frequency the circuit can operate? It will be the maximum clock frequency will be T is equal to, or the minimum clock period will be T is equal to 550. Let us assume that the unit of time is picosecond. So, it is T is equal to 550 picosecond, and the maximum frequency at which this circuit can operate is 1 by 550, right, picosecond, and that will give us a clock frequency, right. Now, the thing is that can we reduce this delay of the critical path? If we can reduce the delay of the critical path, then we can then we can make the time period further smaller, and therefore, we can increase the frequency of our design, right. So, how can we decrease the delay of the critical path? So, we can decrease the delay by noticing that on the other side of the flip flop FF3, we have a delay of only 400, right. So, can we do a transformation in the circuit such that some computational load that is being done on the critical path is done on the other path, because on the other path there is some margin we have, right, because here we have a delay of 550, right. On the other side of the flip flop, we have a delay of 400, right. So, there is some margin left on the other side. Can we shift some computation burden from this path on one side of F3 to the other side? If we can do, then we will be able to decrease the delay of the critical path and increase the clock frequency. So, what is this transformation? How can we do this transformation? So, this can be done using this, right. So, what we have done is that we have moved this AND gate to the other side of the flip flop, but since AND gate is taking 2 inputs, we will have to replicate this flip flop FF3. So, we have FF3A and FF3B, right, and the output of this is fed to this AND gate and then that goes to the FF4, right. So, functionally this circuit and this circuit are equivalent. There is no difference in the functionality, because whatever the output was here at these points, let us call it as X and let us call it as Y, and this is Z, right. So, Z was equal to X and Y. In the other circuit, what we have done is that we have taken X and Y directly at these flip flops, and in the next clock cycle this will be X and this one will be Y and this point will be X and Y, and that will go to the D pin of FF4, and therefore, this circuit is functionally equivalent to the other circuit. Now, what about the delay or the delay of the critical path? Now, delay of the critical path in this case is, for this path we have 500 only, because the AND gate has moved to the other side. On the for this it is same 400, right, and on the other side the delay has actually increased from 400 to 450, yet the maximum delay is 500, right. This is 450, this is 500 and this is 400. So, out of these numbers, the one which is maximum is 500 and that will be still critical, and the maximum clock frequency will be decided by that. Now, in this circuit the time period must be greater than 500 picosecond, while in this circuit, the initial circuit TO must be greater than 550 picosecond. So, here the frequency F1 is equal to, maximum frequency is 1550 and here the maximum frequency is 1 by 500, and therefore, we have increased the operable frequency in this circuit. But what penalty did we pay? We paid the penalty of extra flip flops, right. Earlier we had only one flip flop, right. Now, we have 2 flip flops. So, this kind of transformation is known as retiming. So, the transformations that we discussed are only some of the transformations that are done by the logic synthesis tool during timing driven optimizations. There are many other types of transformations also done by the tool, which we have not discussed. So, if you want to look into more such transformation, you can refer to this book. Now, to summarize in this lecture, what we have done is that we have looked into an important aspect of logic synthesis, that is timing driven optimization, and we also discussed a few important transformations that are done in timing driven optimization. So, after we have done timing driven optimization, our timing of our circuit has improved. But what about other aspect of our circuit, for example, power, right? So, we need to also do power analysis and power optimization in our design flow. So, in the next lecture, we will be looking into power analysis and power optimization. Thank you very much.